presentation content and script done by group members, and voiced by AI.
To get our system running smoothly, we had to tune the PID controller, that's proportional, integral, and derivative. It's what helps the system reach a target value quickly without overshooting or oscillating. At first, the system was either too slow or too unstable. First, we increased the proportional gain, that gave us a faster response, but too much P caused the system to overshoot. Then we added some integral gain to eliminate steady state error, basically to make sure the system settled right at the target. Finally, we tweaked the derivative gain, that helped dampen the oscillations and made the response more stable. After a few iterations, we got a nice balance, fast, accurate, and stable. The system reaches the set point smoothly, just how we wanted. And that's how we tuned our PID controller. A little trial, a little error, and a lot of testing.
Our system doesn't just run, it also monitors itself. To keep track of everything, we set up both online and local storage. For the web server, we used Adafruit.io, a cloud platform that lets us send sensor data in real time. It's simple, reliable, and works great with microcontrollers. We send 3 key pieces of data to the dashboard: temperature readings, RGB color values from the sensor, PID values, and pump speed, which is the PWM frequency driving it. But we didn't want to rely only on the internet, so we also created a local backup, a text file stored right on the device's memory. This file logs the same data: temperature, RGB values, and pump speed. That way, if there's ever a connection issue, we still have a complete history. This way we get the best of both worlds: real-time visibility and secure backup. We have adjusted our algae growth calculations to specifically describe our final closed-loop system setup. Under controlled parameters, with previously found mu equals 0.817 daemon 1 growth rate, consistent nutrient dosing, and ideal light exposure, our algae culture maintains exponential growth. This translates to growth factor 1.264, allowing the population to sustainably replenish itself while supporting the integrated system. Thus, to successfully run our system, we should start with 389, 620, 253 algae cells in our bucket. We 3D printed our own encasing for the OD sensor to block outside light, allowing more accurate and consistent readings. Initially, our RGB sensor performed well. However, it began producing flat values at the final stages. To address this, we first checked all connections and power supply to ensure everything was secure. We then evaluated the sensor's sensitivity and resolution, as insufficient sensitivity can lead to undetected changes in optical density. Recalibrating the sensor was our next step, as environmental factors or drift can impact accuracy over time. We also considered potential contamination or interference. Due to time constraints, we had to conclude our troubleshooting efforts here. We can improve by implementing more frequent calibration checks, investing in higher sensitivity sensors, and allocating more time for testing and troubleshooting. Our OD sensor housing is 3D printed with biocompatible and sustainable PLA. PLA is made from renewable resources like cornstarch or sugarcane, unlike traditional plastics derived from fossil fuels. By using just 20% infill, we minimize material consumption and reduce cost without sacrificing strength. Finally, we evaluated different 3D printers, a Prusa XL and a Bambulab H2D. We used the Bambulab as it requires 38 grams less of material, and it is a quicker print by 3 hours. We reduced not only energy costs, but also the amount of material used. For the system packaging, we chose cork, a renewable, mold-resistant alternative to styrofoam with excellent thermal insulation. We chose to only insulate the algae since the mussels do not need it. With this decision, we also reduced the amount of material used. For the whole system, we reduced it to only 2 pumps, consequently decreasing the energy consumption. Combined, these innovations deliver a sustainable and cost-effective solution.
We're proud to present a fully integrated and operational system. All electronic components function reliably and are properly insulated. The system demonstrates key functionalities, including stable pump control and sensor integration. We also embedded sustainability and innovation in our design, from 3D printed PLA parts to cork insulation. And while we faced issues like pump failures and 3D print mishaps, it was our strong team coordination that allowed us to overcome them and deliver a solid, working solution.